problem's kind of long, so I'm just going to talk you through my solution, and you can, I hope, follow along here. But here we have a car that's going over the crest of a hill, and if anybody's ever done this in their own car, if you go too fast you get airborne here, and we don't want to become airborne, but we want to, this problem it says is what's the maximum speed that he can go over this hill without becoming airborne or without losing contact. So the deal is we want to find out what the maximum speed is such that the normal force pushing up, holding the car from falling this way, so that the normal force equals 0. So what we're going to do is draw a generic free body diagram and evaluate it at both point A and point B. So let's do that. We're just going to draw out here at some intermediate spot. Draw the body here, and we're going to define that mg comes straight down, and that there will be a component of mg going into the hill perpendicular to the tangent. The tangent goes this way, so the perpendicular to the tangent goes this way, the tangent goes this way. So if mg comes down this way, we need to define the angle theta. So if we stretch this down here, we know that from our previous work that rho is the distance between the tangent of the hill at any particular point down to the center of rotation, and we call that rho. And then I'm going to define this angle right here as the angle that it makes with the vertical axis. If this is the angle theta, then that's the angle theta. If that's the angle theta, this makes this the cosine, and that makes that the sine. So I'll put the two components of weight of the mg cosine theta and mg sine theta. And then the normal force always goes perpendicular to the tangent of the hill, so that the normal force is that way. And I think that, and then again, labeling our axis is really important. We draw our t-axis and our n-axis, and then we have our free body diagram complete. Okay, a couple of things we need to establish. We need to establish the slope at a particular point, and if you recall, the slope is dy dx. It is the first derivative of the line, and we know that the slope dy dx is equal to tangent theta. So what we'll do is we'll take the derivative and find out what the slope is at a particular point. So here's the derivative, or here's the equation of our line. We take the first derivative with respect to x. Dy of 25 is a constant, and dy dx is 2 over 200 times x, and so that would be minus 1 over 100x. That's equal to the slope evaluated at any particular value of x starting from here going to this way. So at any value of x we can find out the slope, and we can find out that's the tangent of the angle theta. So we'll evaluate those at both of our points. Let's say that at B, where x is equal to 25, we can find that the tangent of theta is equal to 0.25, and that means that theta is equal to 14.04 degrees. When x is equal to 0 back here, then the tangent theta is equal to 0, which means that theta is equal to 0. The second derivative with respect to x is minus 1 over 100 for both of those. If you just look again at the equation, where we, okay, here's dy dx, and then d squared y dx squared is minus 100 for both a and b. Alright, so then to find out the rho at those 2 points, we're going to evaluate at a first. We're going to say that to find what we're looking for, so we're finding the velocity at a for which the normal force is equal to 0. So the rho, then, we said that 1 plus dy dx, which is going to be equal to 0. That's our slope. Raised to the 3/2 divided by the second derivative is 100 meters. And that's and so then we do our sum of the forces in the normal direction is mass times acceleration in the normal. That's mv squared over rho. So what are my forces in the normal direction? Well, in the positive normal direction, the positive normal goes straight down. That's going to be mg cosine theta. Positive, and then the normal force is going opposite of my positive axis. So I'm going to say that we got positive mg cosine theta minus normal force is equal to mv squared over rho. In this particular case, again, the normal force is equal to 0. So solving this for the velocity, I get v squared is equal to 100, which is the radius times 9.81 times the cosine of 0 degrees, and taking the square root we get velocity is equal to 31.32 That should be, yes, that's meters per second. That's the minimum speed to remain in contact at A. Okay? So if we go faster than 31.32 meters per second, that means we've become airborne. So the key thing here is setting up this equation properly, making sure that the signs, the SIG ends, are correct. Make sure that we say the forces that go positive are the ones that are pointing in the positive N axis. The ones that are negative are going opposite the positive axis. So again, it's really easy to get that confused. All right, next question is, what is the normal reaction of the road when it passes point B? So we're going to keep the same speed of 31.32. We're going to go here to B, and we're going to find out what the normal force is here, the normal force going up this way. All right, so we'll have to evaluate our rho. Same sort of thing. Here the slope in the first derivative is 0.25, quantity squared, 1 plus that raised to the 3/2, divided by 1 over minus 100, and we get the radius, the instantaneous radius rho is equal to 109.5, and the tangent of our theta is we evaluated before was 14.04 degrees. All right, and again, sum of the forces in the normal direction. If I go back to my free body diagram, my normal direction is this way, my positive normal is this way, and my normal is this way. In this case, I got mg cosine theta, and I want to find out what the value of normal is. So I'm going to say minus normal plus mg cosine theta is mv squared over rho. I want to keep that same velocity that I had in the other piece of the problem. I got a different radius, which is 109, got the same mass, and I'm just solving this for the normal force. And when I do that, I get normal, the mass of the car was 1,500 grams, or 1,500 kilograms, and I solved the normal force as 840 newtons. Okay, so I don't think that's terribly hard, but it is several steps. You have to find rho, you have to find theta, you have to take the derivatives of the line twice to get rho, and you have to take the arctan, the inverse tan of those values to find out what those thetas are, and you have to keep track of the positive and negative directions of the normal axis. And so it's quite a few things to keep track of, but that allows us to work smartly through the problem. All right, so here's just a little complication. What happens, or what would you say, is that if the acceleration in the tangential direction was 5 meters per second, what is the force of friction? Well, if we continue with our free body diagram, and now we focus on the tangential direction instead of the normal direction, we would suggest that there's the mg sine theta going in the positive tangential direction and a force of friction probably slowing it down. So I'm going to assume a direction of force of friction. I don't know for sure what it is, but I'll say that I'm assuming it that way. This is my positive direction, so I'm going to say that the sum of the forces tangential is mass times acceleration tangential. I've got positive mg sine theta going down the hill, minus force of friction going this way is equal to m acceleration in the tangential. That's what was given right here. So I'll solve this for the force of friction. I've got m, that's my mass. I got g sine theta minus at is equal to minus 3,940 newtons. Minus 3,940 newtons, which means that I drew my arrow incorrectly. So what it says is that the force of friction, in this case, if I'm accelerating at that speed, the force of friction is actually going down the hill this way. So what does that mean? Is if the force of friction is going opposite your velocity, it's slowing you down. But if the force of friction is going in the same direction as your velocity, that means the force of friction is making you go faster. So in this case, what we interpret then is instead of the driver of the car stepping on the brakes, he's actually stepping on the gas, making the force of friction make him accelerate farther or faster down the hill. Okay. With that, let's do one more problem. This problem is a three-dimensional problem in the NTB system. And so what we've got is a little ball suspended from a suspension point, and it's going around a circle like that. And it says that the mass is 10 kilograms, the length of the rope is 2 meters, there's a tension in the rope of 150. We need to find that angle theta, and we need to find the speed. Now again, this is a very similar to a class of problems that would ask different combinations of these types of variables. So let's just define our axes. Pay close attention here that the ball is not really rotating about that point. The ball is actually rotating about that point. It's going around in a circle like this, which means that this is the n-axis and this is the t-axis, which makes the vertical axis the b-axis. We hadn't done a three-dimensional problem before, but this is a three-dimensional problem such that the n-axis points toward the center of rotation, tangent goes in the direction of motion, b is in the vertical direction. And in these three-dimensional problems, it's very often easiest to make it into a two-dimensional problem by drawing a free body diagram as a plane of this guy. So that's what I've done here. So I've got the length of the rope, got my n-axis pointing toward this way, got my b-axis here, and then t-axis is coming out of the page. A couple of directions or a couple of dimensions that we can interpret from the drawing. I don't know that angle theta, but I know that this length here is L cosine theta. I know that the radius here, the rho, is L sine theta. If there's a tension here, I know that's theta, so that makes that the tension is sine theta in the n-axis and cosine theta in the y-axis or the b-axis. And then the mg of the system, of course, goes straight down. All right, again, we're finding we're finding theta and we're finding velocity. So let's just sum the forces in the normal direction and see where we go. So sum of the forces normal. I'm going to say that we have t sine theta. And if I look carefully at the drawing, that's the only force in the normal direction. So I say that t sine theta is mv squared over rho. And I can solve that where rho is equal to, this right here is equal to L sine theta. Solve that for v squared, and I get that is equal to 150 sine theta times L, this is L sine theta, and where L is 2 and 150 over 10, that's 15 times 2, and that simplifies as 30 sine squared theta. All right. Well, didn't get there, didn't find it with that. So let's sum the forces in the b direction. Now recall again that there is no acceleration in the b direction. We are rotating around here, so we want this to be balanced in the b direction, no acceleration, no movement basically in the b direction. So I'll say sum of the forces in the b is equal to 0. That gives me t cosine theta is equal to mg. When I do that, I can solve this for theta is equal to the cosine minus 1 of mg over t, and I've got some pieces here. I got cosine inverse cosine minus 1 times m is 10 kilograms times g divided by the tension which was given, and I can find that theta is equal to 49.15 degrees. Plugging that theta back into my v equation right up here, and I can say that v is equal to 4.14 meters per second. Okay, well, that gives you a little picture of how to get started with some of these NTB problems, and we'll do some more in class.